So can we start now?
Sure.
Okay. So sorry for the delay. So in this talk, I will share some our recent results about the system design and the performance analysis in effective learning. So there are main four parts, like the privacy and the security issues in effective learning, and we use the blockchain to replace the central server to design a decentralized effective learning. And we do some wireless communication, wireless resource allocation in effective learning in our recently accepted JSAC paper. And we show, I will show some future works and ongoing works. So before we show the something about the effective learning, I want to share our recent paper about the survey in privacy and security issues in distributed learning. And when we writing the survey, we find there is no clear definition about distributed learning. So we began to design or propose a framework about distributed learning. As can be found in this figure, we mainly split the deep learning in two planes, the local plane and the global plane. And between these two planes, there is like the um, aggregation process happens in the global plane. And we split the whole process in according to a machine learning process into four levels, like the data, models, knowledge, and result. For example, in the first level, there are distributed device or distributed users, they have the local data, and they will do nothing but just transfer the data to a central server, and the server will aggregate the data and do the rest of the machine learning. So this is a framework that we propose in the deep learning. And based on that framework, we show in each level there are some attacking and the defenses mechanism in the process. For example, like in the factor learning in level 1, we share models like each user. They use the data to train a local model and share the model to the central server. So during the process, there may happen some like the privacy and security issues, and we'll survey this method and defense methods and their counterparts in that server. So this server is now on the proofreading process, and we will upload it to the archive soon. So now we back to the factor learning. Actually, we began to do some research work about the factor learning in 2019. And we first write a magazine paper published in IEEE network about the privacy and security issue in factor learning. We mainly summarize the privacy and security use like the privacy at the user side, privacy at the server side, and the whole system security problem. And we list some existing or potential methods to protect these metrics, such as the perturbation, like we that the users can add noise or random noise on the local models or local data to achieve differential privacy. And the server can use homo encryption to do a robust model aggregations. So for the first, based on these methods, there are also some issues. The first one is that the factor learning performance convergence with the differential privacy performance. Like if we add a large noise on the models or the data, the privacy level is higher. Maybe we can get smaller optional, but the convergence, the learning convergence will be affected. And there are other issues like the data model poisonings and the scaling up issue that there are a large number of clients attending to the aggregation of the learning training. And we also need to design a robust model aggregation rules. So based on we first do some research work about the factor learning convergence analysis with differential privacy, and this work is published in the TIFS last year. So I didn't list the whole details of these papers, but I list the key algorithm in this paper and the figure set. And in step 7, before we usually broadcast or upload the local parameters or models to the central server, we have a clipping step to clip the local models, and then we add the random nodes on the clipping parameters. So this step is to achieve the differential privacy. And there is the key value. The C is the clipping threshold, which is used to measure the sensitivity. So we then give expression about the sensitivity which is related to the clipping thread C and the bunch size M. Actually, in the Google's paper that published in 2016, the differential privacy with the deep learning, they assume that the sensitivity is 1, but actually in our paper, we think it should have some relationship with the batch size. Also, there is a very useful tool. Okay, sorry. That the Google they keep updating about the differential privacy in machine learning. This is a tool. Yet here is the link that they first in the published in 2019 or 18 that you use the moment account to estimate the privacy estimations. Then in this latest update, for example, we use the privacy analysis. We click the privacy analysis. They actually use the RenE differential privacy to estimate the privacy levels. And the RenE differential privacy is a new method to account the privacy levels, and it can give a tighter DP than the RenE DP here, the RenE DP here, and you can use the code directly in they provide here, and when you inject a NOS power, and you can give very tight privacy levels. So we back to the presentation. Actually, in our work, so we usually think that the sensitivity is related to the bunch size, but in the other words, like the Google or other works that follow the Google structure, they both assume that the sensitivity is to 1. So this is the whole algorithm or whole details about this work. Then we derived some a convergence analysis about the upper bound of this algorithm. So the first part is like the loss functions of the after T communication round, and the omega star is about the optimal loss functions. And in the experiments, we use centralized learning to obtain this value. So there are some conclusions or the findings, like a large epsilon, which means a large loss power will lead to a small loss, and a large number of clients. So the N means that the attending clients will lead to a large loss, and their optimal T exists in we have a certain number of the clients and the epsilon, and we show the experiment result here. And then we, based on the first algorithm, we consider a more practical scenario that in each communication round, there are k of n clients will attending the aggregations or the learning, and we also derive the convergence result. So there are similar but maybe some interesting findings that in there exist our optimal k exist. So we can't so from this finding that we can't let all the clients attending the Federated learning if we consider differential privacies. So there are optimal k, and also we show the experiment result about the loss functions. So this is the first work. And then because we got some findings like the T, there the optimal T exists in the certain N and epsilon. So we, based on that findings, we think about we can dynamically adjust the north powers to find the optimal key, optimal T in the learning process. And we use this out to write another paper published in TMC last year about the whole idea, though the key idea is about we can during the Federated learning training process, we can adjust DP north powers, and when we decrease the north powers, we can it will affect the aggregation T because we have to achieve a total privacy budget. And we gave some design about algorithm designs about this sort. So the key steps we to check the machine learning convergence process. Here we use like a online testing set to monitor the currency. If the currency is not stop improving by two communication round, we will decrease the aggregation time t by this function, and then the it will lead it will affect the adjusting north powers by these equations. And we show some comparison results by this algorithm. There are some benchmarks about for example, the first one is original UDP, which is a blue line. Sorry, it is the purple line that used Google's paper in 2016, and the latest approach in the SP that he also decrease the north powers, but by linearly. And the optimal objective is that in our TIFS paper that we have to obtain some parameter values before the whole experiment. And we can see that the proposed UDP with CRD, the orange one, can achieve most the same performance with the optimal one. So this is our second work. And we also have other works about the different privacy. First one, for example, the one is about the we do some DP in the generated adversary network, and we use RenE differential privacy to estimate the privacy budget. Another point is that actually we achieve the DP by adding dots on the loss functions of distributor, not on the parameters, and we do some comparison result. So this work is submitted to TDIC and now under major revision. And we also do some data level privacy, like we because in usually that like local data in SADE or TKDE that they usually use the Gaussian or Laplace loss to change the value of the data values. But we think about, can we use other records exist in the same data set to produce a random loss? And so this is another idea, and it's also submitted to the TKD and now under major revision. So after these 4 works, we try to broadcast or try to sell our ideas about the private FL to companies or the factories locally, but actually they didn't care much about the privacy. So we think about, we try to change our idea to a robust or secure factor learning. It's like the node is not naturally added on the data processing or the local models. Actually, the data it can be introduced by the imperfect device or sensors, or they are intended device produced by some malicious parties or the, participants. And this work is about the factor learning with unreliable clients, publishing in the IoT last year. Yeah. So we first gave the models about the unreliable malicious clients about 2 parts. The first one is parameter decaying factors alpha, and the second one is like a random noise. So the first one is to describe the intent or malicious behaviors that the malicious clients will aim
sorry,
to.
Dr. Mark, can I have one comment? So I know we have a lot of papers here, right? And
Yes.
I wonder whether we can just follow 1 or 2 papers, because otherwise we will be easily lost. The paper
Sorry.
is complicated. We have a lot of story here. We cannot cover so many papers in like one seminar, right?
Yeah. So my thought is that I want to first give a brief view about our recent works, and I also list some all the published or the paper titles in these slides. So if anyone interested in any paper, I can then maybe give a detailed description or presentation about 1 paper or 2 paper. So in my thought, my audience thought that way, I want to first show a huge or the whole page about our works. So yeah.
Yeah, but for me,
Yeah.
I'm, to be honest, I'm kind of like lost, because I didn't see the logical clues of all the papers. So which one is for which topic, and how we can link these papers, how we have a whole picture. I'm kind of like lost. So if you can give us some hints, say what's the connections, what's the relationship between the papers, and what is the focus of this paper, the focus of other papers, I think it'd be easier for us to follow. Yeah.
Okay. So I will try my best to follow this logic. So yeah, sorry. So the first part is about the privacy, and the first part about the privacy, like we use differential privacy to achieve the privacy protection. And the main method is to adding noise on the local models. So if you read the paper in the Google that in deep learning, they'll use the same way that they add noise on the local models to achieve a DP. So by this method, we do analysis, convergence analysis of factor learning in the first work. So this is the main contributions about the first work. And then in the
wait a minute, sorry, Professor. I mean, I have a question here. So which paper you refer to Google? Which one?
Yeah, I live here. Sorry.
Because based on my understanding, this is very normal clipping. Yeah, if you open this paper, they also use the same clipping threshold with you, and the sensitivity is also is related to C. The gradient is C,
yeah,
and
yeah.
So
Yeah,
I think like what's like you want to say in this sense?
the sensitivity is related to C, yes, but actually we use another parameter M. That you can see that in equation M is like the batch size of each local SGD. So in the Google's paper that they just say that the sensitivity is related to the C, and in the experiment they set the C equal to 1 if you try to find their code. But in our proposal, work, we actually find that the sensitivity should be related to C and the batch size M. For example, M can be 64 or 128. So this is our result. So did I explain the difference?
Oh, I think like the reason like why the sensitivity is related to M here is basically on you clip the model, the local model, and then when you like since the case is when you like for the step step six here is the loss function when you compute over the local data and you get the WIT here, and after you change one data sample and the WIT will change, and in this way it's related to the batch size here, I think. So
yes,
it's because you clip the model. There are people that clip the gradient.
Yeah, I agree with you that if we clip the gradient, the sensitivity should be different. Yes.
And also there is a difference for either average or summation. I mean, when you calculate the sensitivity, like if your loss function is average or your loss function is summation, I mean sum the samples loss. It's actually a difference. So sorry, I still not get the advantage for lemma 1 as a note, but maybe other scenarios or other techniques proposed in your algorithm is better.
What I'm not trying to say that this is the advantage, but we said that if we clipping the results in the parameters, and the sensitivity should be expressed like the following ways. So I'm not sure that it's the advantage, but we say that by this encryption we can get like a tight privacy levels. So did I explain your question? So we can discuss later.
Okay, I understand how do you get the lemma 1, but yeah, I don't know. Maybe before Google's paper, I mean after Google's paper is published in 2016.
Yeah.
16 after after 1 or 2 years, there are a lot of papers related to clipping stuff and using the moment of content method. I mean, so I really cannot find the equation 8 is such kind of new. So sorry for that. I mean,
yeah, okay.
It's fine.
So in the second paper that the second paper that we actually design dynamically north decaying rules to decrease or adjust the north powers in each communication round, and it will return some result like it will return in this algorithm that will, for example, if we find the performance in 2 communication round will not stop improving, and we will decrease the communication round and will return to change the value of the adding nodes in next communication round. So in this way, we found that into different privacy levels, we have a better testing accuracy of performance. So we compare this result with other three methods. For example, the Google's paper, and another non-decaying method published in SP in 2019. So this is two works about the differential privacy in federated learning. And we design other differential DP related works in these two papers. And now we began to show some security issues in federated learning. The first one, yeah.
Sorry for jumping in. Could you go to the decaying one? Jiahao, I think you have you have a paper for the decaying DP noise as well, right?
Yeah, I have, but yeah, what's your question? So
could you go to the algorithm part, Dr. Ma?
Yeah, this one.
Previous one. So could you say it again? So what is the advantage of your proposed algorithm?
So first, we have some observations from the last paper that there exceed optimal T if we have a certain number of the clients' participation in the federated learning, and we add noise on the local models. So we can see that the T, the aggregation time. So now we said why we can monitor the training process or the training performance during the aggregation. And if we find that the learning performance is not increasing, it means that we may be add too much noise during the learning. So we will decrease the communication round. So that the step 8 is like the way decrease the communication round by this equation here. And if we decrease in the communication round, so we have another T because we set a total communication round T, and the T is related to the adding noise in each communication round, the noise power is here. And so if we decrease the T, it will, according to equation 25, it will recalculate a new SDD for the adjective noise, and it will adjust or recalculate the new noise powers in rest of the communication round. So by this method, so we can dynamically adjust the total communication round and the adjusting noise powers in each communication round, and we show the comprehensive result.
If my understanding correctly, right, your DP budget is different. It doesn't change, right? So you just try to allocate the DP noise over different rounds, right? So, but my question is here, you try to reduce the communication round by derive say optimal T or whatever, right? Well, when you derive the T here, do you consider the DP noise added, or you don't consider any kind of DP noise here when you derive the T?
You mean derive the T? You mean here?
When you want to get, I mean, I'm just trying to asking what's the order of this, right? So you derive the T without any kind of consideration of DP noise first, and you try to, for example, that's the first step, right? The second step, you try to allocate the DP budget, you know, over the T round. That's what you do?
Yeah, first we can set a T. We can set an initial T here, and we can, according to this T, we can calculate FTD in each communication round because the nodes can be equally divided, right? So, and during the aggregation, and we can find that if the two communication round, the learning performance is not increasing, so we can decrease the T. So if we decrease the total number of communication around the T, we can decrease it by this equation. Now we can recalculate the SDD in the rest. REST communication round. So we obtain a new STD here. So this.
Okay, that means you need to somehow redo the file learning several times.
But no, in one file learning process, but in different.
Yeah, I mean, if you have a new T, right? So everything changed. So everybody need to resubmit their gradients and adding noise again to submit, do the aggregation again, then and further do the aggregation. So you will say, okay, if this T is better than previous T, until you find the best T, right?
Maybe my explanation is not clear. So for example, the T equal to 50, yeah. And in the first 10 communication round, so they found that the noise is good, and we don't need to change the total number of 15. But in the with the training going that when T equal to 20, we found that so on this stage of the learning, the noise is may be too larger. So it will affect the training performance, and we can decrease the 50 to, for example, 40. So now, because the training process is have finished the 20 communication rounds, so the rest communication should be 20, not 30. So during the rest 20 communication round, they will recalculate the STD. They will add the noise in the rest 20 communication round according to this equation.
Okay, I got your idea here then. So, but you know, who is going to do the optimization? So the local agent,
actually,
they're going to do the optimization, right?
Actually, it should be the server. So, yeah, he monitor the performance, and then in the next round of the broadcasting local global models, he will say that you should to change change the noise power, and he will broadcast also the rest of the communication round, the number of communication round.
Okay.
Yeah.
I think in general case, we adding decaying noise that follows certain kind of pattern, right? For example, we have parameter decaying parameter over rounds. Then just every round you just decay your DP noise. That's it. But here it seems like okay, you connect that to you want to further optimize the round here.
Yes, the goal is to optimize the communication round. So we find a way to adjust the communication round. For example, we can try to set a very large T, but actually in our full result that final result, the T should be smaller than the large T.
Yeah, go ahead.
Yeah.
I have a question here. So, that's like my question is, that's like your algorithm, the epsilon and the delta, the perspective is predefined or it's changed during variant time?
Yes. At the initial stage, we predefined the epsilon and the noise powers, but during the training stage, it will change according to the rest communication around the T.
I mean, I want to say like based on my understanding, maybe I'm wrong, but based on my understanding for different projects, like no matter like Google's paper or lots of papers focus on deep learning with different privacy or fair learning with different privacy something. So the case is they should like first to define how many what's the perspective for algorithm and then to choose the perspective. But
the total privacy budget.
The total perspective you should define first and then to discuss like what's the noise you should consider. But look like your algorithm is you should change. You don't know what's the final user data. But I know there is some paper talks on this way, like how they don't care, they don't know how to stop when to stop their algorithm, and so they do a tracking their parse loss in other way, very complex method. So I don't know.
Yeah, I got
I'm
the
confused.
point.
Sorry.
Yeah, in most cases, right, we have predefined T, so that according to DP composition theory, we can calculate the piracy budget allocation for every round. That's typically what we do for the decaying DP, right? But here it seems like Jiahao mentioned, your T is dynamic. So I mean, it's really difficult to know, in particular for initial a few rounds, how much DP budget you should allocate for the initial few rounds, because you don't know when the algorithm is going to end, right? So you need to, I don't know, you need to leave a certain kind of DP things for future rounds, right? So if both of them are uncertain,
yeah. So we first can have a privacy budget, right? So for example, epsilon for example, epsilon equal to 10, yeah, and we set a T, we set a total communication round T here. So according to T and the total privacy budget epsilon, we can according to the moment account method or some other method, we can get initial north power for each communication round. Each communication round. Am I right?
That's true. If you
the
allocation,
So some equations, some correlations about that equation. So we have 3 parameters: the total communication round T, and north power, and the total privacy budget epsilon. Yes. So now we decrease the total communication around T. Yes. And so we can get a new value of T. So according to the new value of T and the total price budget epsilon, so we can calculate a new north power epsilon. No north power like the delta, the sigma, sorry. So
the reason why I ask you do the fair learning for multiple times, or you only do it one time, right? Most of this kind of things is a one-time thing, so one direction. It's not like you do it for once, you feel okay, the performance is not good, I want to do it again. It's not like that. It's just a one-way thing.
So you mean one way that we doing a whole factor learning process?
Yes. If you fix T, you fix the privacy budget, everybody conducts the fair learning stuff. It ends, just like the time.
You mean that the clients so they at the first stage the client will do like the 50 communication round. We will do the 50.
I regret to add too much noise at the beginning. I want to redo it again because because you need to redo everything. You need to tell the client to resubmit, and I think that's our concern, because most of the time when we do it, we assume a T. If we use a T, right? We assume a T. Like Jiahao mentioned, if the T is uncertain, the question will be very complex. So, but we all follow
I know your concern that
one way idea. It's not like we do it, we come back, do it again, some idea like that.
Yeah, but actually in our case, that first in the first communication, like the 10 communication round, we found that the north power is good, but in the next 10 communication round, we found the north power maybe is too larger. And in the rest communication round, maybe in the whole just one factor learning process, but in the rest communication round, we can decrease the north power. So like we don't need to do it again or do it back to the first stage. but we can do it during the learning process.
Hi, hey, Professor. I will send you a paper. Like it's a privacy meter, pay go or pay as you go compensation. This here they consider like when you adaptively choose the price budget and adaptively choose the iteration you run and how do you compute the price budget. It's not the same as what we usually done like deep learning with privacy. In all these papers, they argue that we should predefine how many iterations we should run and how many what's the price budget we want to achieve. If you want to change the result like first budget and iteration, I mean, by some like conditions, you should like reprove your redo your privacy analysis.
But anyway, I think Dr. Mao, we waste too much time about it, guys. Yeah, we can talk offline, but I think that's interesting discussion because it's. Yeah. Please test the paper Jiahao sent. I think probably that talk about the dynamic but differential budget setup and differential dynamic T setup.
Okay.
Scenario.
So
yeah.
I kind of got to your point that if we change the T, that the privacy level should be changed because yes, kind of yeah. Okay. Yeah. So I will check the paper and we can talk about later or offline. Thank you. Okay. So we're back to the presentation. Is to the security problems. Actually, in this work, the main part is like we model the like the malicious or unreliable clients, and it composed of two ways. First one is like we try to act like the malicious behaviors. He is aiming to downgrade the global performance, like use the decaying factor alpha. For example, if alpha equal to -1, it's completely reversing the signals or local models. And also some attended behaviors like the random adjustment loss by the imperfect device and sensors. So we use like the probability model that each clients maybe have a probability to do the unreliable or malicious behaviors, and we use this equation 5 to do some performance analysis, like to derive the convergence upper bound, like the 7 the equation 7. So here are some assumptions about the convex assumptions or the Leibniz and the smooth assumptions. And to defend or to detect such behaviors, we design a DNA-based detector. It composed of two parts. The first one is like a thin network. He can examine the correlations between two combination rounds, the models of between two combination rounds. Another one is like the MLP network. He can to detect the reverse signals or the decaying factors, and we compare the proposed defense mechanism or defense performance with other three rebuffed aggregation rules. The first one is like the Chuan, the second one like the screw proof, and the third one is like use Pearson relationship to do the online testing. And we can find the proposed algorithm can achieve the better performance. So this whole idea of this paper is like we give a model about unreliable clients in the factor learning performance, and we propose defense mechanisms to say, and then other experiment result about for other data sets. So in this work, we focus on attacking method. We want to design attacking method to in the factor learning. So we first define some goals of the malicious client. For example, he has untargeted goals, and he also have the targeted goals. the target goal is that we can produce some designed predictions. And we also define the background knowledge of the malicious client, like he can know the full background knowledge. He'll maybe know the partial background knowledge that the server have some certain aggregations like the Chrome or the he also know the global model and update from other compromised clients. So we assume that there are multiple malicious clients, and they are a group, or they exist some collusions. And we began to design the attacking goals, like we use like a similar loss functions. So, but this function is like to attacking loss functions. So the attacking goals of these malicious clients is to minimize these loss functions, and they use, for example, mean aggregation rules, like this equation. So the aggregation, the B is the nice or the honest clients, and the M is the malicious client. So they can use the rule to optimize their attacking goals. It's kind of like to train a learning process, but the goal is to attacking, and we can define some attacking goals, like in this film say that we can define the attacking goals to run away from the machine learning goals in this equation, and we derive some result. Also, we focus on the Chrome. The Chrome is a aggregation rule that is select one of the local models that is more similar to other models as the global model. So this is the basic ideas about the Chrome aggregations. And we design a two algorithm about the full background knowledge and the partial background knowledge about attacking method, and also design a known background knowledge with Chrome and or other aggregation rules. I didn't list the very details of this algorithm, but the whole idea is we use iteration search, like the iteration search, to find the theta. So the theta is that the parameters provided by the malicious clients, and if we set attacking goals like attacking functions, we can optimize the theta. And we list the some benchmark and result. The full knowledge and partial knowledge methods you published in the Usanic Security in 2020, and another paper about 2019. So we can find that the proposed algorithm have a highest attacking rate, but because it uses like a iteration search, like a iteration search method, so it will cost a lot of time compared to other method. And we also saw some background, no background result. But the main drawback, though, when we haven't done that, we didn't compare it with like the shadow modeling training with black box attacking method. So we will do it later in the future. And another kind of interesting result, we try to accomplish like a targeted attacking rules. For example, for Minus data set, the classifier know that this is kind of like 9 in the classifier. But if we use like attacking goals that we want to change, we want to let the classifier know that 0 should be 9 to a wrong directions, and we can doing the training, and we can find that in t equal to 200 that the classifier will know that this figure is wrong, and not wrong. He think that this figure should belong to 9, but we know that this figure should belong to 0. So this is our work about like the we design attacking method in factor learning. And this week we try SP this summer, and we passed the first round, but we got some feedbacks, negative feedbacks about the second round. So we resubmit to the TDSC. The comments about the strong assumption about collusions, for example, in the system model that they also the reversing that the multiple malicious and their collusion is a kind of strong assumptions. And now we move to a third part. Third part, like to a major concern in factor learning is about the one-point failure about the central server. So our idea is we want to use the blockchain to replace the central server, and we list a framework here, and we divide the mining and the learning process by steps, and we list some advantages and the issues. The main issue is like now the worker have to do two things. The first one is like the mining. The first one like the training and in the original FL works. And the second one, he maybe do some mining works to that will use in the blockchain. So the first issue is like resource allocation between mining and the training. And the second one is like the security issue about the lazy client, because now we don't have a central server to monitor all the broadcast models, and the like the miners or the training clients will aggregate all the models. So there may be some exist some lazy clients. They will copy the broadcasting models, and then this can be security issues. So according to these two issues, we made other two papers. The first one is in the TPDS about the resource allocations about the blockchain assist decentralized factor learning. And the second one, we want to use PN sequence that used in the wireless communications to act as a footprint for each participant. And this work is ongoing, and we will try to finish by this year. So the last part we do some wireless resource allocation and the user client scaling problems in wireless communication in FL. The object or the goal is to minimize the total delay. For example, the download delay and the uplink delay. So this correlate to the wireless communication part, and the training delay is like the training part. And we have some design. We have designed some subject like we actually the base station didn't know the training results in each communication round, in each client, in each communication round, and each user has a privacy requirement for itself, and we didn't know the channel conditions or for the wireless environment, and we use a multi-ape bandit method to optimize the client scalings. And this paper is just accepted by the GSEC this year, and we have some online manuscripts. So I almost finished my talk today, and we list some future direction. First one is maybe recently very hot in FL is like the resource limit, the factor learning. For example, we have communication limit or training data set limit, and we can maybe use the model compression kind of similar method to serve this one. And we also can use splitting or dynamic natural network to split the training process into several parts. And another fund is personalized FL. We can combine with meta learning with FL, or we research about the model diversity and the similarity or non-IDD data distribution or the uploading time for different clients are different. And the third one is like the vertical FL. The vertical FL is quite hot in China because they already have some companies they use vertical FL with homo equation or SMC, secure multi-party computing, such as the technology to do the project. And also there need some privacy preserving and convergence analysis. Also, they can the current structure cannot ensure a large number of the participants attending in the vertical FL. Typically, the number is maybe like 2 or 3 companies. So there are scaling up issues with robust aggregation designs. So now we also have a large project. It's around 114 million yuan with 10 companies, and we want to communicate with companies and to do some cooperations in or the realizations for the FL system. So that's my talk today. So do you have other questions for the rest of the slides?